right, welcome. Calculus 1. I wanted to talk about acceleration, velocity, and position. You know, we've talked about that. We learned back in chapter 2 or 3, that if you have a position equation as a function of time, you take the derivative, you get velocity as a function of time. If you take the derivative, it's the rate of change of the velocity, that's the acceleration as a function of time. And what we've been doing lately is we kind of start with, here in chapter 5, we start with acceleration and we integrate to get a velocity equation. And we integrate to get a position equation. We integrate velocity to get position. So I want to tell you, I got a couple good problems for you. One of them might be on a future test, this one, and then I'll do another one that might be on your current test. But anyway, so let me tell you this story. This is me. And I was walking, and I was walking around at a pace of 5 feet per second. I was actually walking this way. I was headed back. Actually, hang on, let me switch that up. I was walking this way. All right, I was walking this way, and then all of a sudden, 95 feet in front of me, I see this bear. But my initial velocity is 5 feet per second this way. So I see this bear, see him? And he was just sitting there. So his initial velocity was 0. Well, anyway, as soon as I saw the bear, I turned around and tried to head back to my tent. I thought I could get back to my tent, which was 500 feet away. It was I don't know, I would hope I could. So I ran, I started to accelerate. The best I could was 6 feet per second per second. I turned around and accelerated that way. And the bear immediately gave chase. You shouldn't run, actually, but I ran. Anyway, the bear gave chase at an acceleration of 8 feet per second per second. So that was a constant acceleration. That was my constant acceleration. So you can take the acceleration equations, and I can get a velocity equation for me and the bear. Then I can get a position equation for me and the bear. I think the question is, when does the bear catch me? Does the bear catch me? Do I make it to the tent? Something like that. So let's see what happens. Let's start with me. So if I integrate this number 6, I'm integrating a number 6, I get a velocity equation. And when you integrate acceleration, you get velocity. And anyway, it's easy. You integrate with respect to t. I mean, the notation is I'm integrating this 6 with respect to t. And when I do, I get velocity. But that's the notation, but I'm trying to do it in my head here. I get a 6t. You know, when we integrate, we get the plus c, the arbitrary constant. But in these, I think I've tried to tell you before that the arbitrary constant in these equations is in this equation, it's the initial velocity. In the velocity equation, the arbitrary constant plus c is the initial velocity. And what was my initial velocity? Well, it was 5 feet per second. But if this is the positive direction, we're going to call this the positive direction, then I was headed the other way there. So my initial velocity was actually negative 5 feet per second. So let's fill that in. Negative 5. Again, that's the plus c for this problem. All right, that's my velocity at any moment. Let's integrate to get position. S is position, of course. If I integrate t squared, that's a 3t squared. I integrate the 5t, and then I get a plus c. The plus c is what we call the initial distance, the initial s naught. Now, it's kind of up to you but I'm going to call the bear position 0. I'm going to call, that means I would be at so the bear's initial position is 0. That means my initial position is 95 feet in front of the bear initially. And then the tent is, whatever, 95 plus 550 is, 645. The tent's at position 645 is where the tent is. Anyway, I was trying to fill in this plus c, this plus s naught, and what did you say it was? 95. All right, that's awesome. I got the acceleration. I integrate real easy to get my velocity. At any moment. That's the initial velocity. I integrate that to get the position at any time. That's the initial position. But I've got this function now. This is awesome. What about the bear? The bear's a little easier. When I integrate an 8, I'm integrating an 8. I get the velocity equation for the bear, and it's 8t. Again, it's plus c. The plus c is the v naught, and his v naught is 0. He was just sitting there until I disturbed him. So his plus c is a 0. Let's integrate again to get his position. His position is 4t squared. Is that how you integrate? T squared, yep. Plus that c, which is the s naught, which is the initial position of the bear we decided to call 0. You know, I could have called my position 0, and then he would have been negative 95. I mean, there's a lot of ways you can scale this. Anyway, I chose that to be 0. That's 95, and then that's an additional 550, which is 645. All right, so his initial position is 0. So if the question is, when does the bear catch me, or does the bear catch me, or can I make it to the tent, or whatever it is, I should set these equal to each other and find out what the position is. So here I go. This is fun. I'm going to set this, his position, equal to the person's, my position. And I want to solve this. I think I'm going to move everybody to this side. That'll give me a positive t squared, a positive 5t, and a negative 95 equals 0. And I should probably do the quadratic formula. I don't think it factors. Doubt it. Quadratic formula would be negative b plus or minus the square root of b squared minus 4 times a times c. That's a negative 95 all over 2a, which is a 2. So give me a second. I'm going to pick up my calculator and see what I got here. This is how long it takes for him to catch me. I'm sorry, 25 plus that 4 times 95. And then I want the square root. That's 405. I'm taking the square root of that 405. And I'm getting a 20.12. Let's see, I'm going to add that to the negative 5, add to the negative 5. That's 15.12. Divide by 2. Uh-oh, I don't think this is good news. I got 7.56 seconds. He should catch me in 7.56 seconds. It's technically 2, 3. If it gets that close, I could give it more decimals, but I'm worried. I think he got me. Let's see. I need to know, I mean, maybe I'm in the tent when he catches me, which means he can't catch me. But maybe he, anyway, I should know, I need to know the position. Where was he when he caught me? Where was I? Where was he? I could plug this time back into my position or his position. It won't matter. It's the same. His is easier. So his position is 4 times this t squared. Uh-oh, I'm worried. I think he got me. I think he got me. Square that. Multiply by 4. Oh my God, it wasn't even close. I tried to make it a little close. Should have tried to make it a little closer. After 228.75 feet, I'm lunch. He got me. I mean, it was, like I said, it was 228 feet. Oh man, it was right here. He got me way early. I should have moved my tent closer. I did that right, didn't I? All right, that was fun. Let's do another one real quick. Like I said, it would have been a little funner if it would have been closer, but that was okay. The problem was I was going that way. You could do this problem. Let's say I was headed that way, with an initial velocity going that way, and then I accelerated. That little change in that sign, I think that makes it a little bit closer. We should do that. You should try that again. Try it with a positive 5. Let's just say I was walking this way and all of a sudden I noticed the bear and blah, 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 blah. That would be a positive 5. That would be a positive 5. That would be a negative 5. That would be a, okay, positive 5. Yeah, what would be different here? I'll just do it for you. What would be different here? So that would be... My 20.124 came out of the square root. Now I'm going to add it to 5. 20.1246118. I'm going to add it to my 5. And oops. And I'm going to add it to my 5. And I'm going to get 25. And now I divide by 2. And now I get 12. Okay, let's try this. And now I get 12.5623 seconds. Okay, I wonder what happens now. Plug it. Let's see what his position is now. I'm going to square that. and I'm going to multiply by 4. 631.2. So now his position is 631.2. Does he catch me? Oh yeah, he does catch me. That's his position, that's my position, measured from 0. This is 0. Measured from 0, that's 95 plus a 550. This is at 645. So he catches me at 631, right about there. Damn, I was close. He still caught me though. I should have accelerated faster. All right, let's do another problem. I'm just going to add to this. That was fun. That was a long 10-minute problem, and we kind of did 2 quick versions of it. This one, I like that one. That one might be on a future quiz. This next one is similar to your quiz. Let's say another acceleration problem. Let's say I find myself on this planet. I'm running out of ink on some of these things here. Let's try this guy. I find myself on some unknown planet. Yeah, that's better. Unknown planet. And it has and I don't know the gravity. Unknown gravity. Sorry. Unknown gravity. And so what I do is I pick up a rock and throw it up in the air with an initial velocity of 30 feet per second. And I threw it up from an initial height. I threw it up with an initial velocity of 30 feet per second. I threw it from an initial height of, let's say, 8 feet. And what I did was I timed it to see how long it takes to hit the ground, and I found out that it hits the ground in t equals 44 seconds. So that's kind of a long trip. So I bet the gravity's pretty weak on this planet. But that's the question. Find the gravity on this planet. So the gravity is the acceleration. Again, start with just an unknown a. I mean, I just call it a, but a is unknown. And then if I integrate a with respect to t, I mean, this is the notation. I kind of do this in my head, but this is a constant acceleration due to gravity. Maybe I should call it g for gravity. But it's a, the acceleration, and I integrate with respect to t to get the velocity. Okay, that's at plus c. The plus c is the v naught. The v naught is 30. So there's the equation of the velocity at any time. You take that to get a position equation. The position equation is s. You integrate that. Maybe I should tell you that's what I'm doing. Watch. I'm integrating this with respect to t. Okay, here I go. Integrating let's see, t squared, divide by 2. Don't forget that. A over 2t squared. Integrate the 30t. And then you get a plus c. The plus c is the s naught, which is the 8 feet in this case. And there's the position equation for this object that I threw up in the air. And then this is easy actually. In 44 seconds it hits the ground. So what happens? I can plug in a 44 for t and it hits the ground, so s is 0. This is pretty easy. I can find a. Using that piece of information, I can find a. It hits the ground when t is 44. A over 2, that's 44 squared. 30 times 44. Yeah, this isn't that hard of a problem. I mean, it sounded a little crazy. You start with an unknown a, you integrate to get velocity, you integrate to get position, and now we can find a. A little bit of math here. A little bit of math. Let's see. A calculator might help. 30 times 44. 30 times 44 is 1320, plus that 8 is 1328. I think I'm going to move that over here. It'll be a negative 1328. This is 44 squared. 44 squared divided by 2 is 968. 44 squared divided by 2 is 968a. Well, all I got to do is divide to get a. Here it is. A is negative 1328 over 968. That's the gravity. It is kind of weak on this planet. I'll divide that and see what that is. 1328 divided by 968 is a funny little decimal, negative 1.37. 2, if I want to round it, feet per second squared. That's my acceleration due to gravity, or the acceleration or the gravity, however I want to say it. Gravity is an acceleration. That's what it does. That's what it is. That was cool. I like that problem. You got one on your current little test like that. All right, good luck.